Hello and welcome to section 2.2 of our linear algebra notes. This section will be talking about the inverse of a matrix, and we'll understand what it means for a matrix to be invertible. We'll compute the inverse of a 2x2 matrix, and we'll also talk about how to compute the inverse of a matrix using row reduction. So first of all, a matrix is said to be invertible if you can multiply it by another matrix and get to the identity. And notice that it needs to be the same matrix on each side. We've already seen that matrix multiplication is not commutative, but we do need, in order for there to be an inverse, we need a matrix that does give you the same thing on either side. An invertible matrix is called non-singular, and a non-invertible matrix is called singular. And for 2x2 matrices, there's kind of a straightforward formula for computing the inverse. And you do, so basically you take A, B, C, D, and you do A times D minus B times C. You do 1 over that, and then you swap the positions of A and D, and you put a negative sign beside B and C. And now this formula works if your matrix is invertible. So this is essentially this number AD minus BC tells you whether your matrix is invertible. And one way to remember this, if you try to use this formula and you get 1 over 0, then you know that's a problem because we can't divide by 0. So that will remind you that this formula only works if you're if this quantity right here is 0. And this quantity, by the way, is called the determinant. And we'll talk more about determinants in chapter 3. Okay, so oh yeah, we wrote that right here. Okay, so if we want to compute the determinant of this particular matrix, then we do A times D, so that's 1 times 4, minus B times C, so 2 times 3. And so that's 4 minus 6, which is negative 2, and that's not 0. So A is invertible or non-singular. And if we want to compute the inverse, well, first we do 1 over that determinant, and then we swap the roles of A and D. So we swap the 4 and the 1, and we put a negative sign in front of B and C. And if those were already negative, you do a second negative. So it takes a negative and turns it into a positive, and takes a positive and turns it into a negative. So there's lots of things that the inverses are important for. One of the ways we can use them is to actually solve a system of linear equations. So we have this system here, and if you recall, we can write the matrix equation for this. So remember, we write down the row of things multiplied by x1, the row of things multiplied by x2, then we have the vector x1, x2, and it gives us the vector 5, 2. So if we want to undo this multiplication that we just did to isolate this vector x1, x2, we can actually multiply on the left by A inverse. So we have 1 over negative, and actually, well, yeah, let me go ahead and just write that as negative 4 halves, which is negative 2. Negative 2 over negative 2 is 1. I'm just rewriting this matrix. We have 3 halves and negative 1 half, pulling that negative 1 half through, just to save us a little bit of time as we do this multiplication. So we take that, and we know that this matrix was A, this matrix is A inverse, and then we have anything that we do on the left-hand side, we have to do on the right-hand side as well. So just like with all equations, so we need to multiply that 5, 2 by that A inverse, right? If we had A times X equals B, then we do A inverse times AX. We better multiply by A inverse there. And now this A inverse times A, well, that gives us the identity, since A inverse is the inverse of A. And so we're left with just X equals A inverse times B. So we can apply that over here, and we get x1, x2 equals, and now we do our matrix multiplication. We do our 5 times our -2 plus our 1 times our 2, so we get -10 plus 2, and then 15 halves minus 5 halves. And we end up with -8 and -5. And one of the great things, I'm worried that I did something wrong because it's not what I wrote down. This is not -5 halves. This is -1/2. Okay, so we have 15 halves, and here we have 2 times -1/2, so that becomes a -1. And so actually this is 13 halves. One of the great things in linear algebra is that you can, in this course, you can often check your answers. So if you don't have to, this didn't ask us to, but if you want to check your answers, you plug in x1 and x2 into the equations above. And we see here, when we plugged in x1 and x2, we got -8 plus 13, which is 5, as we wanted. And if we plug in 3 times -8 plus 4 times 13 halves, well, that's -24 plus 26, which equals 2. And most problems in linear algebra, you will be able to do something different to check your answer. So I encourage you to do that, especially as we're learning new material. Okay, so here's this first theorem is just a couple of facts about invertible matrices. If a matrix is invertible and you invert it again, you get back what you started with. If you take two matrices and multiply them together, and then you take their inverse, you do the inverse of the second matrix first, and then the inverse of the first. And what I like to remember this is putting on shoes and socks. So if we have the operation where, okay, first you put on your sock, then you put on your shoe. Well, if you want to undo that, you can't take your sock off until you've taken your shoe off. So it's kind of like you undo the last thing that you did first. So that's how I remember that. And then it does commute with taking the transpose. So you take the transpose first and then take the inverse is the same thing as taking the inverse first and then taking the transpose. And so now we have our first quiz, and you want to think about how you can go about taking the inverse of AB transpose. So this is asking you, what is AB? Oh, and this should all, sorry, these should all be inverses here. I wrote that wrong. So AB transpose inverse equals what? And my hint is use this theorem and also recall from a previous section that A times B transpose equals B transpose times A transpose. So it's a little bit of a hint for you. Okay, so now hopefully you've done your reading of this section. Our elementary row operations, like our swaps and our multiplying by a constant across a row, and our replacement operations, these are all actually matrices. So if we want to figure out what matrix does the job of taking our matrix, like let's say, so in this case we're in R3, so here's what a 3 by 3 matrix looks like. It doesn't have to be 3 by 3, but it does need to have 3 rows. But this is kind of just the easiest way. So if you don't, I'll just, here. Just so you get the idea that this can work on any sort of matrix. Okay. So what we want to do is we're replacing row 3 with 3 minus 5 row 2. So row 1 stays the same, row 2 stays the same, and then row 3 says we take row 3 and we do minus 5 times whatever was in row 2. So this was row 3 goes to row 3 minus 5 row 2. That's what we did. And how would we go about writing down a matrix that did that? Well, we are going to need, so you think about this size of our matrices. We got out a 3 by 2. We had a 3 by 2. And so we're going to need the second entry matches that 3 so they can cancel out. And the first entry needs to be a 3. So we need a 3 by 3 matrix. And what needs to happen on our first row, well, if you think about what happens along our first row, we need to just pick up the first entry, right? We want to pick up this 1 is multiplied by the A1, and then the A21 and the A31 don't matter in our first row. And same thing for our second row. Our second column of our first row. We get the A12 and then nothing else. And actually same thing with our second row. We pick up the second row, but our third one is the situation where we don't need our first row, but our second row we need to multiply by -5 and add that to our third row. Okay, and what you'll notice is that this matrix, one way to think about this is we did the row operation that we wanted to the identity matrix, right? If you take the identity matrix with 1s on the diagonal, 0s elsewhere, and you add -5 times row 2 to row 3, this is what you would get. And so bear that in mind for your first quiz. Your second quiz question, you need to first, I recommend figuring out the elementary row operation that multiplies row 1 by 3, but really we want, since we're undoing it, the inverse, we want to divide row 1 by 3. Or another way to think about that is multiply row 1 by 1/3. So you're looking for what operation does that. Okay, so now we have a theorem and we're going to go over the proof. So any n by n matrix is invertible if and only if. And what this if and only if means is that we have an implication that goes both ways. We have this first statement is true, implying the second statement, and vice versa. So let's first do the forward direction. So A is invertible implies A is row equivalent to IN. And we write that with that little tilde there. Okay, so we know that A is invertible. So that's what we're assuming. And so AX equals B has a solution for every B, right? Because we can always multiply both sides of this equation by A inverse, and you're going to get a solution. We've seen how to do that in the past. But remember, if we have a solution for every B, then there's a pivot position in every row of A. So that means there must be n pivots, since A is an n by n matrix. So that must mean that we have a pivot in every diagonal entry. And so there's only one possible matrix that has a pivot position on each diagonal, because that's going to have, in a reduced echelon form, that's going to have ones along the diagonal and zeros elsewhere. So that's the forward direction. Now and so sometimes this is called the forward direction. And then we have the backward direction. This says that if A is row equivalent to the identity, then A is in fact invertible. And so the way we can see this is, well, we do a bunch of elementary row operations. We do E1 to A. Then that's row equivalent to E2, E1 to A. So like our second elementary row operation. All the way down to, let's say we have P row operations. Okay. So then if you think about what this is really saying, is that this, this sequence of moves undoes A, right? When we do this, we end up getting, so the idea is we do a bunch of row operations until we get to the identity. And so this is the first half of A being an invertible matrix. But now elementary row operations are invertible matrices. You can go backwards. Every time you do an elementary row operation, you can always undo it with another row operation. So that's going to give you another matrix. So these are invertible matrices. And so what that means is we can start multiplying on each side by its inverse. So if we take the following equation, E1 inverse up through EP inverse, times this thing at the top, well, that's going to equal, so we multiplied the left-hand side of this equation by this thing. So we need to multiply the right-hand side by the same product of invertible matrices. And by the way, multiplying by the identity is just giving back your matrix. And if you look here, what's happening is this EP inverse and this EP are going to cancel each other out. And then this EP minus 1 will cancel out with the EP minus 1 inverse all the way through to the E inverse. So what you're going to end up with is that A, in fact, equals E1 inverse through EP inverse. And that's we'll see later, or maybe we see in this section, if you do the reading carefully, that the product of invertible matrices is invertible. So now, finally, if we multiply this A by, let's go back to the matrix that we multiplied on the left by to see that A could get to the identity multiplying on the left. Well, let's look at what A is. Let's plug in the fact that A is E1 inverse through EP inverse, and notice that we're multiplying A times the inverse of the inverse, right? Because when we take the inverse twice, we get back what we started with. And so this winds up becoming the identity. So we have A times this thing equals the identity, and this thing times A equals the identity. So A is invertible. Okay. So finally, let's talk about how we can find the inverse of a matrix using row reduction. So this is kind of cool. We make a super augmented matrix. So normally, remember that we want to do A times X equals B, and we make our augmented matrix looking like that. Well, now we're kind of doing something like that, but we're saying A times C equals the identity. And so just like when we were solving a system of equations, we pulled the A and we pulled the known thing from the right-hand side, and we put them into an augmented matrix. We do the same thing here to find our C. So let's go ahead and do this. And again, in the interest of time, I'm gonna do a little bit of the row reduction with you so that you can see it, see what it looks like with this uber augmented matrix, and then let you do the rest on your own. So you notice we do the same type of thing that we did before, except our goal now is just to get this part to the identity. So we want to reduce this to, in this case, the 3 by 3 identity. So first we need to get zeros under the 1 in that first pivot column. And so we're going to do row 2 plus 3, row 1. And really, you should think about this as just applying row reduction to a matrix and kind of ignore the fact that it's a little bit longer than before. It's just like we're doing it to a 3 by 6 matrix instead of maybe a 3 by 4 matrix. Okay, so we take row 2 and we add 3 times row 1. And we get this thing. And I'm going to combine steps and do row 3 minus 2 times row 1 to go ahead and get some zeros there. So I think that's 8. And then minus 2, 0, 1. And if you keep going, eventually you'll get down to, actually I think we have time. Let's just go ahead and do, there's not that much left to do actually. So we keep row reducing. So now we want to make a 0 in, oh, there is several steps. Okay, but so you want to make a 0 here, and then you want to get these guys to be zeros again, and this guy to be a 1. And so once you do all of that, you should so pause it now. What I recommend doing, just to make sure you're doing okay and understanding this new type of row reduction, is go ahead and pause your video and then come back. What you should get when you come back to us is set this matrix here. And so this resulting matrix is what we want for A inverse. So A inverse equals 8, 3, 1, 10, 4, 1, 7 halves, 3 halves, 1 half. Okay, so now I want you to do the same thing. Go ahead and use row reduction. We don't have to do row reduction for 2 by 2 matrices, but do it to make sure that you get the hang of this. And then what's nice is you can actually check your answer using the formula that we did above, or you can check your answer by multiplying the 2 matrices, right? We could have checked that for this A inverse here and done our A times A inverse, and we should get the identity. So you actually have 2 different ways to check this before you enter your quiz answer. And so you should get a B inverse equals, you know, something, 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 and we want the first row, second column entry. That's not a 0. This is saying this is the entry that you want to enter.